may have. So just before I delve into the research, for those who of you are not aware of RMIT, so RMIT is a very old institution in Australia. It was actually established in the late 1800s as the Working Men's College, and it was mainly a vocational education institution. It was granted a university status only in 1992, and it still continues to have both higher education as well as retains its vocational education as well, and that makes it the biggest institution in Australia, biggest university by student numbers. So RMIT basically has around 100,000 students enrolled in both higher education and vocational education. So it's in where we are based. It's based in the middle of the city, about 2 to 3 kilometers walk from the NCG, and quite well located with public transport as well. So now, sort of jumping into the center. So one of the hats that I wear, I'm the director for the Center for Opto-electronic Materials and Sensors. It's one of the 7 university mandated leading research centers at RMIT. And as you see, I've put up the names as well as the specializations of some of the key leaders. And what you will notice here is that the expertise is quite interdisciplinary. So I am an electronics and materials engineering by background, but as you will see, the expertise on the slide is quite varied, and that will also reflect in the projects that I'm going to talk about. It's deliberately very interdisciplinary in nature. So our research focus areas are not limited to what's here, but you can primarily put that all of that under these categories. I'm not going to read out everything, but I'll move on shortly. But essentially, what we do is in a way depicted in this flowchart. So we start very fundamentally at growing ultra-thin materials, primarily two-dimensional materials. We typically use, mostly vapor phase, but also liquid phase, depending on the application scenario and the deployment scenarios. We use a chemical vapor deposition, and recently we are about to establish a laser-based chemical vapor deposition facility as well. We perform our fundamental investigations right at the top and the middle of that flowchart, where we are growing the materials, characterizing their properties, tuning their optical and electrical properties, but then we also apply them across different application areas. So I've only picked on a few. The projects that we do are quite broad in terms of the number of applications that we're tackling, but I'll talk about a few as examples. So a lot of you who may have worked with two-dimensional materials or maybe working with these type of materials would have often heard that these materials are really rich for its fundamental properties. You can discover new physics and understand its properties at a fundamental level, but it's not scalable. That's not really true. So I'm going to talk about a few projects as examples where we are actually using these two-dimensional materials in an industrial context and scaling up different types of devices based on these materials. So again, I won't go through everything on this slide, but I've put a very few examples of the kinds of industry partners that we are working with in different application areas. And through the presentation, I will touch on some of these application areas in a little bit more detail. So one of the areas that we work on are chemical sensors, so which are large area detection of trace chemical compounds, primarily of interest for improvised explosive devices. So what you see down the bottom right of this slide is a chip designed and fabricated at RMIT. You will notice that there are multiple, so each of the rectangles are multiple sensing elements with its own individual readouts, as well as a multiplexed readout on a chip carrier seen in the top part of the figure. So we basically do all the bottom-up design, from the design, fabrication of the sensor, testing, and then utilizing machine learning as well as later on artificial intelligence to make predictions as well once we have a large amount of data that we can train the machine learning model with. So that's sort of one area that we've been working actively, and this project is funded out of the Australian Defence. Another key area that we've been focusing on is neuromorphic sensors. So this figure here represents our inspiration for it. So let me start by giving an example that will illustrate the problem that we are trying to address here. So our cameras in phones, the digital cameras, DSLRs, or even hyperspectral sensors that are currently put, say, on autonomous platforms or satellites or drones to image particular features or areas of interest. They are similar to how your normal cameras work. So they will collect images frame by frame, mostly redundant. So you collect a lot of data, terabytes of data sometimes, and then you have to send it to a memory unit and then send it to Earth if you are in space, and then perform processing. So what you're doing is basically shuttling data between three discrete blocks. So you have the sensor, then you have the storage, then you have the processing, and a lot of the data is actually redundant because you're looking at the same pictures and frames again and again. Especially in environments which are size, weight, and power constrained, it's a massive problem. And because of the sheer volume of data, often the real things and features that you're looking for gets missed, or if you pick them up, there is no way you can intervene real time because it takes a long time to actually process that data and come to a conclusion. The second thread of this problem is actually the computational resources that are needed. So data computation now consumes about 10% of global electricity output. So when you hear that, we have to make transistors smaller and smaller to make them faster, yes, but I think in 10 years, we would not be constrained by the amount of transistors on a chip or the number of transistors on a chip. We'll probably be constrained by the amount of energy that is available to actually process the amount of data being generated. So that's sort of coming to the problem from another angle. So what we've been trying to do for the last particularly 8 or 9 years is look at the human vision system as an inspiration. So how the human vision system works is at the front end, you have your cornea and the retina. That's like a visual information photodetector, but not everything that your eye sees is transmitted to the brain for processing. And that's part of the reason that the brain is extremely efficient in processing the information that it gets. 80% of the information that the human brain gets is from your vision. So what happens in the eye is your photoreceptors actually capture the visual information, but the retinal neurons and ganglion cells, and there's a range of anatomical processes happening, pre-process that data. So it cuts down redundant information, it packages the information in a much more compressed form, and only then it's sent to the brain through the optic nerves. And the time lag between what your eyes see and your brain perceives is about 20 milliseconds. And a big reason for that is that this information is actually cut down. So the idea we were grappling with is, can we actually mimic this to reduce the amount of data being processed and subsequently the energy, and can we just build something that focuses on the features of interest? Now, I'm not going to delve too much into the biology, but this slide just essentially shows that the human brain comprises of neurons, and how the neurons work is through synaptic potentials. So there are calcium ion channels that connect different neurons through synapses, and these calcium ion channels strengthen or become weak based on the strength of the electrical potentials that we generate. So there are two kinds of potentials. One is an excitatory postsynaptic potential, which is sort of positive pulse of voltage, and then there is what's called hyperpolarization and inhibitory postsynaptic potential, which makes the connections weaker. So these are sort of very basic neural functionalities of how the neurons operate to process and retain information. So when we started many years ago, we just investigated a very simplistic device based on a mechanically exfoliated black phosphorus crystal. Um, Nothing that is scalable, and I'll come to the scalability aspect. But fundamentally, what we saw there is when we shine one particular wavelength of light. Um, Let me see if I can grab a laser. Okay, so one particular wavelength of light, you see a jump in current, which is expected when you shine light and there are photogenerated carriers. However, at another wavelength of light, we actually saw an opposite polarity. Uh, Now, the physics behind this took us quite a bit of time to sort of understand. We believe that now it's governed by trap states with dynamically formed defects on the surface that trap charge carriers. But the important thing was, we could actually, just by switching the wavelength of light, obtain both the excitatory as well as the inhibitory potential. So what we then ended up doing was a series of experiments to show that the device could mimic simplistic, very simple neural models, the Pavlov's and the Hebbian learning models. So these involve basically illuminating the device with different pulse widths of illumination. The key here is sort of this relatively slow decay of current, and what this allows you is a memory time window to actually run a classification neural network which you can train to recognize certain features of interest. So just jumping to this slide, we basically created a neural network that could harvest data from the device, and we could train it to recognize simple patterns and images. Now, mind you, this was data coming from just one single device, and the neural network was running on a computer. And this was the start of, in a few slides, I'll show you where we are at the moment with that. So we basically benchmarked the device parameters to the standard Pavlov's and Hebbian learning models, looked at both excitatory and inhibitory potential. We also transferred the device onto flexible platforms and showed that the operation can still occur if you want to put this up on a mechanically conformable platform. Then, as a next step, as I said, we were discussing black phosphorus earlier. One of the problems with black phosphorus, obviously, is it degrades in the environment through photooxidation facilitated by humidity. We published a series of papers on how we can actually protect the material from this damage. So I'm not covering that series of papers in today's talk, but moving on to what we've been doing with this neuromorphic sensing work. So from a single device, then we moved on to different materials that are active in different wavelength ranges. So this is an example of a 4x4 pixel array that you can see in the image that we created. So 16 sensing elements. And we basically projected simple alphabetical letters, showed that you can retain that information for a few seconds, and that sort of time window gives us an opportunity to run classification neural networks for pattern and image detection. More recently, we've also been able to showcase more dynamic gesture recognition. So not just static image and pattern recognition, but also dynamic gestures. Say, for example, hand waving gestures and patterns, very simple ones. So where we are at the moment, as I just showed you, we went from a single device, then we started looking at different material systems, and based on the wavelength of operation, we can grow these materials, carve out pixel arrays, create the circuitry around it, and now we have reached a 64 by 64 pixel array. So this is 4096 elements on this small square area. rest of it is readout circuitry. As you would appreciate, these are not just digital sensors, so it requires a lot of mixed signal processing and circuit architectures around it. And 64 by 64 gives us enough resolution to actually project different kinds of images, like real world. We have built the optics around it to project it onto the sensor chip, similar to how you have a lensing system in a camera, and then perform this in-sensor computation as well where needed. So as I said, there are challenges. We're scaling it to high density pixels. We're starting to look at motion feature extraction as well, and tailoring materials to operate in different wavelength bands, all the way from UV to the infrared. So as you would appreciate, when we're looking at different materials, so we are also looking at their ability to detect different parts of the spectrum. So this is some work that we did in creating tin sulfide and showing that this material could be a relatively broadband photodetector, all the way from UV to the near infrared. This was published in Advanced Materials a few years ago. In this particular case, we actually used the liquid metal exfoliation. So we basically had a molten tin in a sulfurized environment where tin sulfide layer forms at the top, and then you can basically transfer it off as around a 1 nanometer thin tin sulfide. We have been looking at transition metal chalcogenides, WS2, MOS2. So here an example of MOS2. So what we demonstrated in this study is, as you can see at the top, just under the tube, we grew MOS2 crystals, monolayer crystals, using slightly different parameters. So essentially what we did is control the amount of oxygen that is present during the synthesis. When you have a lower pressure during the synthesis process, energetically MOS2 tends to harbor sulfur vacancies. And when you have more oxygen in the system, this oxygen actually passivates those sulfur vacancies. And that's what we are calling atmospheric pressure, because there's more oxygen in the system. And what we compare is, by slightly tweaking the amount of oxygen in the system, we are able to actually quite significantly change its electrical and optical properties. So if you look at the field effect transistor example down the bottom, when there are more sulfur vacancies, you have a negative threshold swing, because sulfur vacancies introduce negative charges, so you expect that to have an n-type doping effect. In the light detection domain, when we compare that, what you see is when you have more sulfur vacancies, now these defects essentially trap carriers, so it increases the recombination lifetime, so you get a much higher level of photocurrent. However, if you compare it to the oxygen passivated one, the difference is, the oxygen passivated MOS2 tends to have a lower photocurrent magnitude, but faster rise and fall times. So the message here is that by controlling the amount of oxygen during synthesis, you can create both electrical and optical signatures that you require. If you want slower decay, for example, in neuromorphics, you can engineer more oxygen vacancies in the system. Then we moved on to study the effects of these sulfur vacancy defects and oxygen passivation on the piezoelectric properties of molybdenum disulfide as well. So again, we performed a series of tests using AFM as well as devices prepared on a PET substrate and subjecting them to different mechanical bending cycles. We essentially also created an energy harvesting circuit and showed that these are not artifacts. We can actually harvest this energy to power very small devices like LEDs. And now we are working with industry on creating piezoelectric paints that can power, small street lights in parks around Melbourne. So it's again sort of translating into that industry space as well. Uh, so again, post that, we are also looking at growing different angles of bilayers. So what you see up the top is 0 degrees and 60 degrees. We can go 30 degrees as well. Obviously, those who know CVD, we can't really control the angle at this point down to very small angle variations. So what we can do is an overlap 30 degrees, 60 degrees, and with that overlap we see a stark difference in the electrical and optical properties. So I put the papers down at the bottom if you're interested. We also looked at lateral junctions, so you would have seen a lot of um, bilayer junctions, vertical junctions of materials. What you see down the bottom left is essentially actually a planar junction of MOS2 and WS2, and there's an atomically sharp boundary that we have at that junction that creates a built-in electric field that we can utilize to you know trap charges, create different types of phenomena. So again, I've listed both the papers down the bottom. If you're interested, I'll be happy to share the slide deck with you later as well if it helps. Then we also look at strain manipulation of different properties in these different types of materials. So we can fabricate materials on flexible platforms as well, strain them, both positive and negative, and look at its optical and optoelectronic properties. Now, this is an example of a project that we did with Carl Zeiss, and at the start of my talk, you might recall I mentioned in some cases we do liquid exfoliation as well, and that is governed by the application area. So this is one such application that we worked on where we required liquid-based materials. So Australia has a huge problem with skin cancer, or skin carcinoma, and what we did here is basically prepared molybdenum trioxide inks. As you would see up the top, generally speaking, they're transparent visually, but then we benchmarked it to the Fitzpatrick table so for 6 different skin types, because the UV tolerance threshold is different for different skin types. So we benchmarked it for 6 different skin types, then essentially integrated that into a polymer matrix and put that on a 3M backing tape. And down the bottom figure, what you see is, okay, if at the start it's relatively transparent, but if it's turned dark blue, that means it's time to get out of the sun, put more sunscreen on, take preventative measures. So it's more of a qualitative color changing patch that we created to warn the user that, okay, you need to take measures to now protect your skin because you've had your safe threshold exposure of UV. This is a project that we're working with a smart home manufacturer in Melbourne who basically use a lot of glass in their houses. And the idea here is to create smart coatings on glass. We're using the electrochromism principle here that you may be familiar with. And the idea is not just to change color in the visual to block or allow light, but more importantly, also have the ability to control how much infrared radiation you can allow or block. And the idea and the modeling of this company shows that if in summer we are able to block the heat carrying infrared radiation on demand, and in winter allow more of it, the heating, ventilation, and air conditioning costs and consequent emissions can be reduced by 30 to 40% depending on the scale of the building. So this is just a small lab-based demo that we have done, and we're now scaling this up on 1 by 1 meter glass panels. As you can see, we have an electrolyte here, which we are moving to solid electrolytes now, but basically applying small voltages and changing its optical properties. So again, just to showcase that there is a lot of room to work with industry in different application areas. Now, before I end, I also wanted to showcase an example which was more accidental in nature rather than planned. And the reason for showcasing this is, again, you might have noticed I was talking about interdisciplinary expertise in the center. where we have electronics, AI people, but also microbiologists. So here is an example that comes out of just having microbiologists in the center. So the black phosphorus that we investigated for a few years for its electrical and optical properties, um, and as I mentioned, it's quite reactive to atmospheric conditions, particularly in the presence of light. um, so what happens is it's really good for electronics and optics in the lab, but when you're trying to scale that up, it becomes a problem because you don't want the semiconductor to decay in performance in a couple of days or 3 days and stop working. However, it turned out that when we were investigating the mechanism of that degradation, what happens is that this black phosphorus produces reactive oxygen species that degrade its surface. It turns out that these reactive oxygen species can actually be used to target drug resistant pathogens, both bacteria and fungal cells. So, we have actually published a series of papers, filed patents, and now spinning out a company in this space where we are utilizing this material into gel formulations for infection healing in wounds. So this was something that, just as I mentioned, came out of just having different types of expertise within the center. So we basically did a lot of animal trials, so mice models. And as you can see, what we did is compared the wound healing in mice using standard hospital treatments that are currently saline or antibiotics like ciprofloxacin, and BPNFs is essentially black phosphorus nanoflakes. And as you can see, that the wound heals much better and much faster compared to the current treatments. We are now, as I said, in the process of spinning a company out for wound healing applications, and then validate this in porcine models as well, which are a bit more expensive and more time consuming. So we will get to that. But the core aim of sort of showing this slide is, uh, the reactive oxygen species were a problem in electronics, but a big advantage in microbiology. So just sort of thinking out of the box and having different expertise really helps identify those opportunities. So just a quick word about the second hat I wear. So last year, the Australian government invested in an industrial transformation hub for intelligent contaminant sensing in complex environments. So I am leading this center comprising of 5 different universities and 17 industry partners. So it's a quite a big hub. And one of the key features of this hub is this integrated research program. So in program one, we are looking at creating the new types of sensors, the sensing surfaces, and essentially the hardware, sensing hardware. Program two is focused more on the signal processing and AI for prediction. So how are we harvesting the sensor data and making meaningful conclusions, and can we predict contamination hazards based on that data before hazards actually occur? This program three is actually quite unique. So this is we deliberately brought in a social scientist. So this is not a technology person, but a social science person who is experienced in end user uptake of technology. So this person is going to actually talk to the absolute end user of the technology and document their needs and feed it back into program one and two, so that when we actually validate something in the lab, it can be deployed in the real world. Most of the times, things work brilliantly in the lab, but just fall apart even before going to the real world. So that's the aim of having that overarching program three in place. So this hub is just about to actually start next month or the month after, and it's a 5-year program funded by the Australian government. Um, just a quick note about the facilities. So RMIT has a suite of facilities. Most of the facilities at RMIT are centrally managed and controlled. Everyone has access to them. We have a large clean room spaces with all of the semiconductor design, modeling, and fabrication and packaging facilities. And then we have different smaller testing labs depending on what tests that you want to do and validate. So happy to discuss any opportunities where you think this could be of use. And before I end, obviously this is probably 1/4 of the people of the center available for a photo, but a big thank you to all the PhD students, staff, and research fellows in the center. They are the people who do the grant work, and obviously to our funding partners as well. And with that, I will call the presentation to a close, and hopefully I have left enough time for people to jump in with any questions that they may have. Thank you very much.
Thank you, sir, for such an interesting talk. Sir, while the participants ask their queries, I have a couple of queries which I like to ask. Sir, while working with the two-dimensional transition metal dichalcogenides like molybdenum disulfide, you said that by controlling the oxygen environment, you are trying to control the sulfur vacancies. So, but while we were trying to grow molybdenum disulfide, the issue we faced was if we increase the oxygen content in the CVD chamber, so the molybdenum disulfide layer starts to etch out. So how do you control that amount of oxygen such that the nucleation overcomes the etching?
Yeah. So Poonam, a very valid question. So obviously, as you indicated, we can't keep continuing with just increasing oxygen. So there is an optimized window within which this passivation works. Beyond that, if you continue increasing the oxygen, etching is one aspect. The other thing is you actually start getting a lot of surface oxidation as well. So it's not MOS2 anymore. So it required us a lot of optimization to just identify that, if you want to call it a sweet spot. And that spot will vary in different systems based on how your system is connected up, how well you can control the pressure as well. So we cannot certainly, as you said, increase the oxygen indefinitely.
Sure, sir. So, and the same thing like the oxygen content, like to create a particular number of sulfur vacancies, the oxygen content will vary for a like for a monolayer as well as for a multi-layer film.
It will vary, Poonam, because if you have, for example, a bilayer system, with the bilayer systems as well, what we have found, and it's a little early days, but what we have found is the first monolayer that you grow, the amount of defects that you create in that monolayer dictate how the second layer grows as well, because defects also introduce lattice strain in the lower layer. So there's a lot of growth dynamics that we need to play around with, certainly. And um, every system, and this is like coming back to a lot of people who use sputtering as systems, different sputtering systems have to be optimized to grow the same material as well. It won't be the exact conditions that will be replicated from one system to another.
Yes. And sir, one more thing in the heterojunctions, like over the WS2 layer, you were trying to fabricate an MOS2 layer. So how do you take care of the direction and alignment during the synthesis process?
So the planar layers, Poonam, the one that I showed, which was planar, to be
Yes.
honest, we created it by accident. We were not planning for that, and there was a and it's what we believe is it's just that, again, a combination of your flow rate, um, and the precursor amount that you're using, and where in the tube the precursors are placed. So there are specific spots that you get that.
Yes.
And then we basically investigated its properties. So again, we didn't think of doing it. It was by, and we continuously got this structure when we were optimizing it. So we thought, okay, let's investigate its fundamentals and the atomically sharp boundaries that we were getting.
Okay. Okay, sir, I get your point. Sir, one more doubt. Through your IC sense at Industrial Hub, you are working with contaminant sensor. So, how do you take care of the drips that occur while working with liquid sensors? Like in case of suppose we test in water or aqua solvents,
Yep.
then how do
So,
you take
so
care of that?
yeah. So basically, for one of the projects that we are working on in that hub is going to be with the water industry, which is looking at on-site sampling of E. coli. So currently, how it's done is chemical assays are done. Water is sent to a lab, like blood is sent to pathology, and pathogens grow during the transit itself. So you don't really get the real uh, aspect. What we are doing is creating different materials, selective functionalization layers, and then building circuits around it so that you can get sampling done on site. So again, we never build a single sensor. We build 30 or 40 different sensing elements and a machine learning algorithm that is harvesting that data from each of those sensing elements and giving an on-site inference that, okay, there is E. coli, there will always be E. coli in water. What is sort of the threshold of that? And then if you are collecting samples, say, every week over 3 months, is there a trend that is indicating that there is some contamination or cross contamination with sewage, that there could be a health outbreak coming? So,
Okay.
so that's sort of the kind of project that we're working on in the water. In terms of the sensors, the water industry is essentially after um, chips that can be used a few times. So what we do is, as I mentioned, we create arrays, and on each measurement they use just one single line of the
Okay.
sensors. The next time they use another line, the next time they use another line. So they can still use it many times before they have to change the sensor.
So, but using it multiple times, like suppose you have a single array and you use a single line of sensors, but the values you get, like the values in whichever unit you are recording, those values will drift with number of times you repeat the experiment. So, is it the ML modeling which is taking care of the drift in that case?
Yes, so we have comprehensively modeled drift and noise within
Okay.
certain bands. And the other thing is we don't simply just look at the change in the at the raw numbers. So we don't look at the raw numbers that, okay, this is the current that it reaches. We actually look at delta I and translate that into, we have amplification circuits around it and current to voltage converters, but we have comprehensive modeling for noise as well as drifts in current.
Okay, sir. Thank you so much, sir. Now I would request the participants to ask their queries to the expert by switching on their audio and video and first by introducing themselves.
Good morning, sir. I'm Animesh Paul and from IIT Indore. Sir, my question is that in the first part of your slide, it shows that in a black phosphorus materials at a certain wavelength, it shows excitatory response, and at a particular wavelength, it shows inhibitory response. Sir. Now, sir, excitatory response is understandable because photocarriers are generated and that contributes to the current. That's why we get raise in current. But how to understand those inhibitory response, sir? And how to optimize that particular wavelength in case of inhibitory responses?
Yep. So very good question, Animesh. As I mentioned in our study as well, it took us a very long time to actually understand that. We did a lot of mathematical modeling as well. So what we found is with black phosphorus, particularly in the UV wavelengths, because one of the mechanisms to create these reactive oxygen species on the surface is actually photo-oxidation. So I didn't cover that series of papers as I mentioned. So with that particular wavelength of light, uh, it produces the most efficient way of creating these reactive oxygen species that start acting as hot electron trapping. So when that happens, the charges being generated are trapped in those hot electron traps dynamically, and then you start seeing that sort of opposite photo response. Now, it is extremely hard to actually have an experiment directly showing
Yes.
that this is happening. So we did, chemical assays under different wavelengths. We did, as I said, mathematical modeling. You'll see in the paper that I mentioned we published. And then we did a series of experiments with other wavelengths of light as well, where that was not happening. Uh, in other experiments, we kept the black phosphorus under inert conditions as well. So we did a lot of sort of indirect experiments to come to a conclusion that it's sort of those dynamic trap states that are being generated, particularly at that wavelength.
Okay, sir. That's why, because I am trying it with MOS too, but I did not get any particular wavelength at which it's
So
associated.
we have been trying with MOS2 as well. It's
Yeah.
not a trivial thing. Black phosphorus has this unique interaction with light and oxygen. To It's actually degrading in the process. To be honest, like it's
Yes.
mechanically degrading. So if you keep that light on for, I don't know, for 4 to 6 hours, you will actually see that it's mechanically shrinking and bubbles starting to form on the surface. So again, we have a very good series of publications in that area as well, where we systematically look at how different wavelengths of light change the surface of black phosphorus.
Yes, sir. Thank you, sir. Thank you very much.
Good morning, sir.
Morning,
My name
morning.
is Vikas Kumar Verma from IT Indore. Sir, as we know that the pristine 2D like MOS2 or WS2 shows the less selectivity for other gases. It shows the selectivity only for the NO2. But from the literature, we have seen that the defect density or doping enhance the selectivity of the 2D materials. But we can do the doping as per our requirement. But I am unable to find a way to control the defect density. Is there any way to control the defect density via CVD growth? Or
Yeah. So I think if you are wanting to very firmly control the defect density to a level that you want to quantify the defect density, I think it's very challenging with CVD, especially
yes, sir.
with thin film furnaces. Now, can it ever be done? I don't want to say no. So, as I mentioned, we are looking at also, we're currently establishing a laser based CVD as well. So, we feel that it probably offers a better control because you are not going to rely on uniform heat distribution in the CVD to break down your precursors and generate those defects. In a laser based CVD, you're going to rely on laser power. So you're using a KRF XMR laser to actually break the precursors down. Now, how controllable that would be, we will know in time. But I think you can create a relative sort of, yes, low, medium, high. But if you are really after putting numbers to it, I think
Yes.
it's going to be extremely challenging.
Sir, in one research paper, I have seen that they have annealed the 2D material after the growth in presence of oxygen and in absence of oxygen.
Yep.
And they have shown that the defects are created differently in both the ways, as they have created the oxygen vacancies and oxygen vacancies reflected to the defects.
Yep.
But there is no any method to control it. That's why I asked you if there is
There
any
is
way.
none. There is none to control it. So, what you can do is sometimes work backwards. So, for example, let's say you are looking for a particular photo response or
Yes,
optical
sir.
response. So, you could, for example, if you have some sort of an environmental chamber where you can also probe, you could do annealing in different controlled
Yes,
environments and in situ do measurements to make sure
yes,
that you stop at where you want that response to be. If you were to sort of do the reverse way and say, I want this response, do I have the exact parameters in the CVD that engineer this response? Um, the answer is no. It's not that controllable to that level.
yes, sir. And one more thing, sir. As you have shown the different structure of the 2D materials in the growth process that was accidentally received, we were also trying to synthesize the WS2 via APCVD process, and we have received the 13 different structures and interesting structures. Like there is one monolayer in same orientation, and above that the second monolayer structure is oriented at different angles,
Yep.
and similarly many more angles, many more different structures we have received. but we are unable to quantify their properties in terms of the sensing or any other thing. Is there any way?
Yeah, look, we are happy to discuss if there is, something that we can add. So I work a lot with different institutions in India where, they have the samples, but we are actually characterizing the devices and their performance. So we can also do, for example, one of the things is in these materials you have this inverse symmetry in the crystals as well.
Yes,
So we have second harmonic generation that we use to characterize that as well. So we have all of that setups that we do as well. So happy to discuss a bit more. In fact, I will be at IIT Indore for a conference in person next month, I think.
yes, sir. Rupesh
So
Diwan, sir.
Yes, sir.
yes,
It's
yes. So happy to discuss there as
Yes,
well.
sir. I will meet you, sir, and I will show you the different structures I have received. And also, sir, we have tried to define their properties by the theoretical study like DFT, but none of our collaborators were able to complete that DFT because of the different structures.
Yeah.
So I will
So
try
as
to.
you said, if there are too many structures, I would
Yes,
assume DFT people will push back on it because just simply because optimization of structures does take a lot of time and resources.
yes,
So
sir.
we can have a look at it. Sometimes it's not important to do a DFT calculation on all the structures that you're growing. It depends on what you are trying to actually show with the DFT.
Yes, sir. I will show you the structure in IIT Indore whenever you will visit, sir.
Yeah.
Thank you so much, sir.
thank you, sir. I'm unable. Yeah, go ahead.
Hello, sir. I am Mohit from HNRG Group. I had few queries regarding the real-time decision-making application. Sir, how did you design that system, cross multiple optical junction and im- uh, applying light, you as you shown in image 532 maybe green, and with different pattern, did you get different currents? And with current threshold, you are getting whatever these results. No?
So thanks, Mohit. So short answer is yes. So obviously we engineer different materials to, and that's based on if you want to do the imaging and inference in the visible wavelength or the infrared wavelengths. Um, Now the structure around it is a lot more complex to describe. So essentially, what you have is in the final 64 by 64 that I was talking about. Uh, you have 4096 elements with their individual readouts, but also multiplexed readouts. You would appreciate that you're dealing with very low magnitudes of current, so there are noise mitigations built into the circuit as well to ensure you are reading above the noise floor. um, and then we first validate any data, so you can actually pre-train a neural network. We first validate it on an FPGA platform. So we connect the whole sensor up to an FPGA platform, validate the neural network, and now we are actually building circuits that carry the neural network as well, so that we don't need a computer to do that. So it's a combination of materials, a lot of EBL and deposition. So we use electron beam lithography to get that sort of density of electrodes as well, and then the processing, the image sensing or the projection. Maybe I went through it too fast, but we have built lensing systems to project the image onto the sensor area. So similar to what your cameras have. So there is a sensor inside, but your lenses actually collimate the image and project it onto the sensor. So we do that part as well. So there's a lot of sort of different small parts to it that are integrated.
So basically means after acquiring each junction current, there is a TIA or with multiple.
Sorry, Mohit, your voice is cutting up, but can you repeat?
Sir, actually, after getting each pixel output current, multiple TIAs integrated with the microcontroller whatever, and you are getting currents, and with the help of mapping, you will decide whatever pattern is recognized.
That's correct. That's at a high level. That is correct.
Besides,
Besides,
I
I
designed something like that with few junctions, but initially by just 4 by 4 junction with completely on hardware level with TI and STM microcontrollers. So I am facing a lot of problems like how to on multiple laser beams on different junctions and these problems.
yeah.
Just
Obviously there are, as I said, a layered number of challenges that you have to resolve. So TI is just one part. When you're using amplifiers, bear in mind it also amplifies the noise. So it doesn't just amplify the signal. So there are techniques and strategies that you need to put in place, and just at a high level without knowing exactly what you're doing. Just even how you are creating your grounds matter here, because it's not just digital in nature. You're using a lot of analog electronics as well. So that, as I said, it's a very layered problem, and you might have problems in one or multiple areas of the circuit.
Sir, I will meet whenever you are in IIT Indore. Then I will show you whatever I am. So
Sure, no problem. I'm happy to visit and have a look at labs, whatever can fit in that duration that I'm there.
thank you.
Are there any questions for the participants? They may raise their hands or just switch on their video and ask their queries. So, do we have time? Like, we can take a couple of more questions, or
I think a couple of more questions happy to take, and then I have to jump into a meeting.
yeah, sure, sir.
Yeah.
So, we'll see if there are any questions from the participants. So, I can see in the chat box there are no questions and no hand raises from the participants. So, I think we are done with the queries from the participants. With this, I'll come to a formal conclusion of the today's talk.
Thank you so much for
the invitation.
I'll share my slides. So we had a very enlightening session by Professor Walia. I would like to thank our speaker, Professor Sumeet Walia from the Department of Electrical and Electronics Engineering, RMIT University, Melbourne, Australia. Thank you, Professor Walia, for such an interesting talk. We are grateful for the time and efforts you took to share your experiences with our IEEE community. With this, I would now like to request everyone to switch on their videos for a virtual photo session. Yeah, thank you, everyone. Thank you, sir.
Thank you.
Thank
Thanks,
you.
everyone.
So we are happy that you would be there in the next month here in India at IIT Indore. We'd be happy to interact with you and gain some knowledge from you.
Thank you so much, everyone, for your time.
Thank you, sir.
Thank you.
We are
Bye.
waiting for your
Thank you, sir. Thank you, sir. Yes.
Thank you, sir.